So we're moving into chapter 3, which is called Polynomial and Rational Functions. We're not going to be dealing with rational functions so much at all. We're going to be dealing with polynomial functions. And pretty much the point of this chapter, for our purposes, is going to be to learn how to graph polynomial functions. So first, we're moving into section 3.1, which is quadratic functions and models. So we're going to first start with just quadratic polynomials. Quadratic polynomials. First of all, a polynomial is a function. The book says a polynomial function of degree n is a function of the form, and then there's this form of a generic polynomial there. So I'm going to use that as well. So a polynomial, polynomial of degree n I should say a polynomial function. We can talk about polynomials outside of the context of functions, but we've done so much function work that we're going to talk about polynomial functions now. Okay, so a polynomial of degree n is going to be just some or difference of terms starting with an x to the n term. So if I said of degree 5, then the leading term would have x to the fifth, so the exponent being 5. I'm leaving space here, and then plus the next term down. The next term down would be, let me start over, goodness. I'm trying to leave space for the coefficients and I'm getting mixed up. Okay, the next term down, if we put it in descending order, should be the next lowest exponent, right? So like x to the 5th, x to the 4th, x to the 3rd, 2nd, 1st, all the way down to x to the 0, which would be the constant term. So I'll say, since I don't know what n is in this generic form, I'll put ... and then my next to last term is the linear term, the one with the x to the 1st. So x to the 1st, and then the last term is the constant term, which I'll say x to the 0, because recall x to the 0 is just 1. So this is going to be the constant term. So what about the numbers that can be attached to the front of the x's? How do we denote that? Because we want to be able to say that they can be any real number. Okay. So how do we notate that? Like just generic numbers. I could put like A, B, C, etc. But that would limit me to 26 terms. But this, this could be any n I want. It could be bigger than 26. So the way I notate that is I put an A and then I subscript it with an n. So this index is not an exponent. It's just saying like this is the nth coefficient. And then here, so this is the n minus 1 index there, a sub n minus 1. So that's the n minus 1th coefficient. This is just a way to keep track of potentially, tons of terms. So down here, this is a to the 1st, and down here is a to the 0. We call this term here, we would say this is altogether the leading term, because it has the highest exponent. We call a sub n alone the leading coefficient. So each of these little a's are just representing a number, so a coefficient. Back here, a sub 0 x to the 0, that's just the same as a sub 0, right? It's just, we just put the x to the 0 there to emphasize that we're going all the way from n all the way down to exponent of 0. But it's really not necessary because it's just 1, so I could really remove it if I wanted to. This is the constant term. So the term at the back that has no x attached to it. Okay. So in this section, we're going to be looking at quadratic functions and how many, when they're simplified, how many terms do quadratic functions have? At the most, they have 3 terms, right? The x squared term, the x term, and the constant term. They could have less, right, if the constant or the linear term is 0. A quadratic function is a polynomial function, so it falls into that category of things that I just wrote down a second ago, of course. It's just a special polynomial function that has a specific degree. Of course, the degree is 2. And the way we write a generic polynomial, a generic quadratic function is we could say p of x. Since we know there's only 3 terms, we can just notate the coefficients using like alphabet letters instead of like a sub 2, a sub 1, a sub 0. I can say ax squared plus bx plus c. So why not just use like a sub 2, a sub 1, a sub 0 like I did for the generic polynomial? Well, I mean, that's a good question, honestly. We could do that, but maybe this is just more comfortable for students. Maybe that's why traditionally we write a generic polynomial function with coefficients a, b, and c. It's especially nice because c is the constant term, right? And constant starts with a c. Now, of course, if you go outside of a degree 2, then you've got to use different letters, right? Like a linear thing, we use mx plus b a lot, or ax plus b. Or for a cubic thing, you would need ax squared plus bx plus c, ax cubed plus bx squared plus cx plus d, right? So just notation here, that's all. And we will replace p of x with just a generic f of x. Okay. All right, so the goal of this section is to go on a deep dive about graphing quadratic functions and also possibly modeling with them. We'll look at that. We'll look at that. Okay, so we're going to go on a deep dive about graphing quadratic functions, but you already know a fair bit of stuff about graphing quadratic functions. So what do we know? What do we know about graphing quadratic functions? Well, from 2.6, section 2.6 about transformations of functions, I know that if I have f of x equals, say, like x minus 2 all squared, then that is a parabola that's been shifted right by 2. And how did I ask you to sketch a graph? Last time I said as long as you can figure out where that beginning point is going, right? So right here, then just kind of sketch the rest of the shape that you know a parabola should generally have, right? But we didn't really worry about, like, we didn't go into any more details, right? Obviously, there's a lot more we can say because I'm back in 2.6. I said, just kind of make sure it's got a general U shape, make sure the legs are pointing the right direction and all that. So we know about this. We also know that if I do something like, say, x minus 2 squared, and then I add a 1 outside of the function, then that results in a vertical shift. So I know that it's going to scoot right by 2. And it's going to go up by 1. So that new quote unquote beginning point right there is going up by 1. So over 2 up 1. So now the parabola is starting there. That's the new shape. We also know that they can, if I add inside the parentheses here, that means a scoot to the left instead of a scoot to the right. And if I subtract outside the parentheses, that would be a scoot down as opposed to a scoot up, like the example I've given here. But what else do we say? We can say, I know that if I stack a number out front that's bigger than 1, like say 5 times x minus 2 all squared plus 1. Oh, sorry. Then that's the same as having that parabola in the same spot, up 2 over 1. Nope, other way around, sorry. Over 2 up 1, over 2 up 1. So you see I haven't changed that vertical horizontal shifting. But if it's got a number multiplied on the outside, that's going to, and it's bigger than 1, stretch it vertically, right? So it should get like, oh, that's maybe a bit of an exaggeration, but it should get more narrow, like it should grow taller, faster. Yeah, it's maybe a little bit of an exaggeration. Maybe it shouldn't have been that steep, but that really gets the point across that it's getting vertically stretched. What else? We know that if we multiply outside by something smaller than 1, like a fraction less than 1, then that widens the parabola, right? It squishes it down horizontal, or squishes it vertically, so it would get wider, more like bowl-shaped. And then also we had the negatives on the outside. And what did that do? So we didn't really do any that put all of this together, but now that we're really digging into quadratic functions, we're going to want to know how to do this. We're going to want to know, well, lots of other things, but we're going to want to make sure we know how to graph something that culminates in something like this. So it still goes over 2 up 1, and it's still going to be very, compressed or stretched vertically or compressed horizontally like this shape. But when I negate the outside here, the outside, not the inside, but the outside, that flips it over the x-axis. So I should have something more like this, flipping this upside down. Okay, now the question is, wait. In general, we want f of x, which is equal to ax squared plus bx plus c, because we don't know how to graph something like that when it's in that form. To be in the form, this form, right? Because if it's in this form, we can graph it. And in fact, we'll learn that we can say even more about this form than we did in 2.6. Like I can say more about this. We'll get to that. But the goal for a lot of this section is going to be to get things that are written like this to be in the form. And I'm going to use some different letters here. A is the same. A is going to be the same here. And then I'm going to have x minus h all squared. So that's going to represent the horizontal shifting. Could be positive or negative, but built in with a minus sign there. Plus some other number out here, k, for the vertical shifting. Okay, let me say a little bit more about that form. I'm going to rewrite it here. This form is called standard form. And again, why do we want it? Because we can graph it easily. Well, relative to how, we should be able to graph it because we have techniques from 2.6 that tell us how to graph things in this form. You know, you got your horizontal shifting, you got your vertical shifting, you've got your number outside that could be negative. Okay, this is called standard form. We say, now recall that with these examples back here, just looking at H and K, so ignoring A, just looking at H and K tells you what that little point is going to be, the beginning, and what I've been calling like the quote unquote starting point of the parabola. So for instance, in this case, that's 2, 1, right? 2, 1. We say that, now I'm going to give it a better name here, because starting point's really not a great name. We say that that coordinate point, h, k, from the generic form, h, k, but see how that lines up with 2, 1 here, right? H, k is the vertex of the parabola. Vertex of the parabola. So if I was to draw just a couple little examples here, just in the first quadrant, just to keep it easier, some point out here H and some point up here K, and then maybe I have some parabola centered or vertex at H, K pointing up. This would be the case of f of x equals a times x minus h all squared plus k, where what? Where a is positive, right? Because the parabola is pointing up. So that leading term, that leading coefficient would have been positive. That leading a term is positive. And you see here that coordinate point is h, k. That's the vertex. Okay, then I could have another case where maybe I have the same h and k. I have the same h and k, but this time the parabola points down like this. So this is this form, f of x equals a times x minus h squared plus k, where a is negative. Where a is negative. Where a is less than 0, in other words, a is negative. So I did a couple of these back here, right? I have the positive f of x, 5 times x minus 2 squared plus 1. There's that example, and then negating it, and it flips it over. Just showing you here, I'm just showing you what these letters are doing, right? The h and the k and what the a does. So the h and the k control where the vertex is. And the a controls, you can't really see it here, but a controls how vertically stretched or vertically compressed the parabola is, and also what direction it's pointing, up or down. Okay. But this is all assuming that we have the function written in this form. This is all assuming we have the function written in this form. How do we get to that form? So let's go on a discussion about that. How do we get question? Okay. So we need to do some preliminary stuff before we begin our discussion about the transformation of this to that. First of all, I need you to be able to recall the formulas a squared plus 2ab plus b squared is equal, and these are different a's and b's, okay? This is just different, just using the same a and b for a different thing here. That the perfect square polynomials, perfect square trinomials in particular, there's two forms of those. There's the sum, a plus b all squared is equal to this, and a squared minus 2ab plus b squared is equal to a minus b all squared. So I pointed these out a while ago, but just recall that the way to be able to recognize these, is you have to note that the two outer terms are perfect squares. Like, let's say I have x squared, something like this, and I'm going to fill in the middle term here. I say, oh, look, the two outer terms are perfect squares. Obviously, x squared is a perfect square. It's literally got it in the name, right? X squared. And 36 I recognize as a perfect square number. And the central term should be, should be twice of the product of a times b. What is b in this case? If b squared is 36, then b must be 6. So this middle term should be 2 times x times 6, so twice of x times 6, so 12x. 12x. And that's going to be equal to x plus 6 all squared. So why am I making a big deal of this? Well, probably you can see that this is a just generic polynomial form, which is what we've got here. And this looks promising. It's in this form a little bit, right? It's got the x plus or minus some number squared, right? So this is, you see how this is going to be a critical part of the one of the big pieces getting from this to this. In fact, it's pretty much the big idea, getting from this to this. Let me give you some more examples here. X squared minus 14x plus 49. So sometimes it's hard to note that central term and say, oh, that's twice of the x times the, square root of the last term. That's like a mouthful, right? Maybe it's hard to recognize that. But just look at the outer terms, right? Look at those outer terms. That should be your first check. Like, oh, look, this is x squared and 49. I know that's, it's a perfect square number with a root of 7. And then go and look at this and say, oh yeah, that's double 7. That's double of 7. So this must be x minus 7 all squared. What about x squared minus 15x plus 49? Can you do anything with that? Two outer terms are perfect squares, but that central term is not double. So maybe this could be, you could do something else with it, but it's not in that form that we need. So it's not in that form that we need. But what if our, we'll have some things not written very nicely as perfect square polynomials. We're going to discuss the method to get from a generic quadratic polynomial to a perfect square polynomial. But first, we just need to be able to make sure that we can recognize when they are in the right form. Here's another one, x squared, let's say, plus 18x plus 81. So hopefully you see that the two outer terms are perfect squares. And then you're thinking like 9, right? You're thinking of a 9 because square root of 81 is 9. And then you're thinking, okay, if I double 9, do I get 18? Yes. So this one is good. This is x plus 9 all squared. And the sign is dictated by whatever the sign on the linear term is. See, plus, plus, minus, minus, plus, plus. Because the outer term should always end up being positive. And anything that gets squared in this form, right? Either form, the outer term should be positive. Okay, so there's some examples of those. This is going to be what we need to be able to recognize. Okay, so now let's talk about moving a function from f of x equals ax squared plus bx plus c to, I'm just going to rewrite it since I'm on a new page. This is the goal. This is the goal right here. All right. So in general, these may not be perfect square trinomials. In fact, in general, they won't be. They really won't be. All right, so let me find a good example. Some of these problems go a little bit too crazy right out of the gate, so let me see. Let's see. Let's see, I think that's a good example, x squared minus 2x plus 3. By the way, we're not thinking about factoring these. Not really. We can talk about factoring them to find their roots. That's going to be part of the discussion, but I'll talk more about that in a minute. So for now, we're just focusing on getting this thing into a form like this. Now, something to note right off the bat with this one is that a is equal to 1, right? So a is not going to be a problem for us here, right? Don't need to worry about a, it's just 1. Okay, so what I do need to worry about is the fact that this is not a perfect square trinomial, right? It's not a perfect square trinomial because this 3 is just, well, it's not a perfect square. Okay, so what can I do? What can I do to this function that would make it a perfect square trinomial? So what you should be thinking is, how could I complete this quadratic polynomial, x squared minus 2x, and then with some term here, some constant term here, so that when I write it in this form, or rather, what I'm trying to say is that it will be in this one of these perfect squared trinomial forms. In particular, this one would be the this form with the difference there. So what number must b be? What number should I put here? Something that when I double it, it gives me a 2, and also it needs to be a perfect square. Well, how about 1? How about 1? Okay. So maybe you're thinking like, oh, okay, I kind of see, like now I see how you got 1, because if I double it, it's a 2. And also 1 squared is 1, so it's a perfect square. But how the heck could I figure that out, right? Well, we'll get there. So this would be x minus 1 all squared, which is exactly what we want, right? Okay, but what's the problem? It's not a 1, it's a 3. It's a 3, right? It's a 3. So what I'm going to do over here to this polynomial, this one, is I'm going to add that 1 in, like literally force a 1 right there. Literally force a 1 right there, and then bring my plus 3 down. Now, as this stands, as I've written it here, this is not a legitimate thing to do. You can't just add to a function like whenever you want, right? You can't just add to it. What do I have to do in order to bring balance back? Because I've unbalanced this. It's no longer the problem I was given. So how do I bring balance back? Well, if you add 1, subtract 1, right? I'm going to subtract 1 back here. So essentially I've done nothing. Like if you were to combine like terms here and clean this up, it would get right back here. But I've added 1 in a very sneaky way by putting the plus 1 up here next to the rest of the function pieces that, you know, the degree 2 and the degree 1 terms. And why have I done that? Well, because that, to me, tells me now that I can take these three terms and write them as x minus 1 all squared, and then I'll just have this extra stuff on the outside, which is perfectly fine. And look at that. We set it all up. It's a big setup, right? But then it gets right to this form. And now I know exactly where the vertex is. So I could graph this pretty quickly now. So I know where the vertex is. I'll write down where it is. It's at 1, 2, right? 1, 2. Flipping the sign on whatever's happening here. 1, 2. So now I could graph this fairly easily, which is pretty substantial, right? We could not have graphed this beforehand, right? We couldn't, well, I mean, obviously we could do it with a graphing calculator or something like that, but we didn't know how to deal with something like this outside of using a graphing calculator. Like, we didn't know how to graph it by hand, but this process lets us get to this form, which we do know how to deal with. It's a parabola that's been scooted right and up 2, right by 1 and up by 2. In other words, its vertex is at the coordinate point 1, 2. So really the tricky part is getting here, right? Understanding what you need to add or subtract, or well, rather what needs to be added into the function to make that part of it a perfect square trinomial. So let's do another example. The first example in the book goes pretty intense, so I'm going to do quite a few like build-up problems before I start with their example. Let's see. Let's take another. See if you can get it in the form. It should be some function. Again, a is 1 here, so we want some function like x, and I know that this is going to be minus here because, oh wait, sorry. It's going to be plus. The sign is dictated by that term there. That term there. This sign doesn't matter. This number is going to end up changing. Don't worry about this number. We're worried about. Okay, we're worried about this stuff here first. So see if you can figure out what needs to be added to this equation so that you can say x squared. So what am I saying here? I'm just trying to tell you to find the number that you would add right here and then have minus 1, and then you would subtract it again. So this number that would make this part here a perfect square trinomial. And I will be right back. All right, so either you pause the video and tried, or maybe just took that time that I was away to figure this out. Let's see, what could we add here? What could we add? It doesn't hurt to just start trying some numbers, right? Like maybe off on the side, like just thinking about this part of it, x squared plus 4x plus something, and I'm thinking it should be x plus something all squared. Maybe you're thinking like a 2, right? Because a 2, you should be thinking like, what's half of this coefficient here? What's half of this coefficient? It's 2. Does that work? let's see, put a 2 there. What happens? Well, this outer term here, the constant would be 4, because remember, the number you're looking for gets, the back term gets squared, right? This isn't b, this is b squared. So you're trying to think of what b is going to be. B is going to be 2. Does that make sense here? You could even multiply this out and check and make sure it matches this. Make sure it matches this. You would square x, you would square the 2, that works, and then you would take x times 2 and then another x times 2 term if you multiplied this all out, and you would get 4x. So 2 is going to work here. 2 is not what we add though. Okay, 2 is not what we add. 2 is just going to be the result here in the factored form of this perfect square trinomial. So we're going to add 4 and subtract 4, just like that. Earlier I said we would talk about factoring these things. Let me clear up the air on that a little bit. What I meant is this part is factoring. We are factoring a small portion of this polynomial into a perfect square trinomial. But probably when you think of factoring, you think of starting with the beginning and trying to think of two numbers that multiply to give this, that add to give that, and trying to get it as two different factors. That kind of factoring, like more traditional factoring, we might use in this section. But for now, again, we're just focusing on this portion, getting from this to this. Okay, so what do we have here? Well, we have this part, x squared plus 4x plus 4 is a nice perfect square trinomial. Now the rest is just a consequence of, you know, just the sum of these two constant terms. -1 minus 4 is -5. Why is this so useful? So I can say plus -5, or I'll just say -5 there up in the corner. Why is this so useful? Because now if I wanted to graph this polynomial, or rather quadratic function, oh, I'm going to need a bit more than that going this way. I already know where its vertex is, and I can just kind of sketch a graph from there. Where is its vertex? I should go left by 2, right? So its vertex is going to be at x value of -2 and all the way down at -5. That's its vertex. I'll move my hand in a second. There we go. Vertex is at -2, -5. Which way is it pointing? Well, it's pointing up, right? That leading term a here is positive. A is just a +1, so it's pointing up. And I've drawn my little arrow for the vertex in like perfectly the wrong spot. So I'm going to draw it in green so we can see that over. You know, maybe it's something like this. You know, what would be some other stuff that would be useful to know about this? Probably where it crosses this axis, right? So I could like put a point here, probably where it crosses the x-axis, right? Those are some other things we'll be looking at. But I know this is probably the trickiest part. So we're going to keep working. We're going to keep working at this. Now, maybe you're thinking like, I'm starting to get it, but I just don't see how I could ever come up with these numbers, right? Without tons of time and basically just trying tons of numbers. So is there a process? Yes, the answer is yes. Is there a process that can help with, I'm just going to write this polynomial quadratic function and then the vertex form, aka standard form. Whenever I learned this, I called this vertex form, but now this book calls this standard form. So if you ever hear me say vertex form, I'm referring to this. To me, it makes a lot more sense, because, well, this tells you the vertex pretty much immediately, hence why I called it vertex form. But anyways, I should say standard form, because that's what our text uses. That's what the homework will use, and, you know, all the problems you'll see. in WebAssign and in the text and in the exam. This is standard form. Okay. No, that's a question. Is there a process? Yes, there is a process. First, let's just consider the examples we've been looking at where A is 1. So very special case, but let's start there. Let's start with A equal to 1. So we want to get from x squared plus bx plus c to, see how I'm just letting A be 1. Oops, x minus h all squared plus k. These are like the previous two examples I've done where there's no non-1 leading term. The leading term is just 1, right? So it didn't really play a big role. Let's look at those. Oh, excuse me. Let's look at those previous examples. We had f of x equals x squared minus 2x plus 3, and that culminated in being equal to f of x equal to what was x minus 1 all squared, and then plus 2. So you should note that it's the k term is not really a problem, right? The k term is always just a consequence of what you had to do to manipulate to find the h term, or yeah, h term. So the k stuff is not, you know, the k just comes from whatever the constant is already there, and then you subtracting to balance out your function to what you did to the function in order to get it written in this form here, in the perfect square trinomial form. So really what we're going to be looking at, we're going to be emphasizing how to get that h term. So let's see what we did. Can we deconstruct this? Let's make a note here. Let's note that how did we find the -1? One of the things I pointed out was to say that this term in half, I said, what do you double, right? That's how I put it. What do you double to get a -2, or just a 2, right? Or -2. What do you double? You double a -1, right? So note that -2 over 2 is equal to -1. And this is what ended up in here. And this ended up being our h term. Also, k was equal to the original constant term plus -1. Right, because it equals 2. Okay, so what am I trying to say here? Well, I'm trying to say something, but let's look at the other example, which was x squared plus 4x minus 1. So I had, I'll do it in a different color. X squared plus 4x minus 1, and that yielded an x plus 2 all squared minus 5. All right, does the same idea work here? Let's see. Note that taking that central term, which we could call b, right? B, but for now I'm just writing it as what it actually is in this case, which is a 4. And I said, what do you have to double to get that number, right? So in other words, taking half of it, and I get 2. Okay, and that ended up being, hang on, I just realized I made a mistake here. Technically, I should say back here, the negative one ended up being our negative h term, just because I don't want you to get confused about, like, it directly matches what's inside the parentheses. Like this -1 should match here, -1, and +2 matches here. But I don't want you to get confused about, wait, isn't h supposed to be like automatically negative, right? So if I wrote that completely clearly here, what I would say is that -1 is actually negative h. So what I mean is, so technically h is equal to 1 in this case, right? Because h already, this form already has a minus sign built into it. So h is technically 1 here. But the point is that if you take half of the central term, you just end up with the thing in already stacked in the parentheses, like x minus 1, or in this case, x plus 2. So technically, in this case, I can point out that technically h is equal to -2 here, right? -2. If we want it in this form where the inside has a subtraction built into the formula. Also, what can I say about k? K is equal to our original constant term in this problem was a -1. Wait a second. Oh, dang it. What did I do? Oh. Sorry, 1 second. I'm checking something. 3 minus 1. Oh, right, yeah. K minus 1 plus 4. No, sorry, plus -4. Let me rewrite that. -1 plus -4 gives me -5. That's the thing that we subtracted off the back, right? A -4. If you go look back at that problem, here, I'll show you. We subtracted a 4 to balance out the 4 that we added. Okay, so what's happening here? We see that taking half of that central term gives us what should be in the parentheses. But what about the k term? Well, we have to be a little bit more careful there. Okay, we have to be a little bit more careful. Let's see if we can write down some rule in terms of these letters, B and C, and then H and K. Okay, some generic rule. All right, because I said the question was, is there a process, right? Is there a process that can get us there? And the answer is going to be yes, and we are first investigating where a is equal to 1. So what are we going to do? We're going to take f of x equals x squared plus bx, and we're going to add something. We're going to add something and subtract something. So I'm going to leave a little space, and then I'll put my plus c. Then I'll add something here and subtract something out here. What am I going to add? And the point is that it should end up in the form x plus, what did it end up being? It ended up being half of this central term inside the parentheses, right? Whatever b was over 2. In the first case, it was 2 over 2, giving us a 1. Or actually, it was a -2 over 2, right? So it ended up being -1 inside. In the second case, it was a 4. 4 over 2 is 2. And it was positive, so we put +2 inside. This is what we want. But technically, what are we adding? We're adding double this, right? Or actually, sorry, not double. We're adding this thing squared. Right, we're adding this thing squared up here, so plus b over 2 all squared. We're adding that, and then we're also subtracting it, minus b over 2 all squared, minus b over 2 all squared, which looks a lot worse, right? But this is what we end up with down here. Inside the parentheses, we have half of that linear term, and then outside, it's a little bit, we really need to be aware of what was added, right? So that we know what to subtract. There it is. That's the formula to get from this form to this form with a equals 1. So as you can imagine, it gets a little bit more complicated when a is not equal to 1, but this is all we did, right? This is all we did for the first two examples. Let me show you. So maybe I'll rerun them using this nice, easy little formula here. So if I say f of x is equal to x squared minus 2x plus 3, b, which is really what I'm concerned with, is equal to -2. So I should have f of x equal to x plus -2 over 2 all squared plus c minus -2 over 2, that term squared. Oh, sorry, c is 3. Dang it. C is 3. And then cleaning this up, I get x minus 1 all squared, right? -2 over 2 is -1. And then plus, what is this? So this is just a -1 squared, which is a 1. So 3 minus 1 is 2. So it gets us there. Now, maybe you think this process is like maybe more difficult. So then just kind of crunching the numbers and figuring out what it should be. What should be added and what should be subtracted. But traditionally, the way this is taught is by this process, to add and subtract something like this to the function, and then to factor this part of it into a perfect square trinomial, and then to just deal with this, you know, whatever this is just some arithmetic back here. No factoring or anything like that, right? Just crunching some numbers. This is how this is traditionally taught. In fact, most instructors, I think, don't do a separate case with a equals 1. I just wanted to kind of build up to the generic case here. So now that we've done a few with a equals 1, I think we're ready to look at one where a is not equal to 1. So let's consider f of x equals 2x squared minus 12x plus 13. Okay. So first thing we're going to want to do is pull the 2 off of the leading term and the linear term, the quadratic term and the linear term. So step 1, let's see. So step 1 is to say f of x equals 2 times x squared minus 6x and then plus 13. And then what we're going to do is we're going to work inside the parentheses to find that term that should be added and subtracted to both sides. What should it be? Well, since now inside here a is equal to 1, I'm just working with this like x squared minus 6x part, right? What do I add to this to make it a perfect square trinomial? I take half of my central term. What was it? Remember? Half of the central term. Half of the central term, so b over 2, and I square it. That's what gets added here. So I'm going to add half of -6, whoops, sorry, I'm thinking ahead. Half of -6 and then square it. So x squared minus 6x plus -6 over 2 is -3 squared is 9. So this is coming from -b over 2 squared. Just for this little inside part. Once you get rid of, or well, we didn't get rid of it, but once you factor off the leading term, right? So I'm not dealing with, like, b back here is 12, right, or -12. But I don't want to deal with that. I want to pull the 2 off of here up front so that this is now a 1 right here, so I can just work inside the parentheses. Just working inside the parentheses to find that perfect square trinomial. So my next step, I've got 2 times x squared. I've figured out what needs to be added inside the parentheses. I'm adding that 9. And now you might say, okay, so that means to balance this out, I subtract 9 out here. Why is it not subtract 9? It's very close, right? You got the right idea if you're thinking, yes, I need to subtract something on the outside, but I'm not subtracting a 9. If I truly want to bring balance to this, I need to subtract 18. Why? Because the 9 I added is buried inside this parentheses that is all being multiplied by a 2. So why subtract 18 when a 9 was added? Right, I added a 9, so why aren't I subtracting 9? Because the 9, the plus 9 in there, is being multiplied by a 2. The 9 is being multiplied by a 2. Cool. So that pretty much sets me up here, right? I'm set up with my perfect square trinomial. I've just got to do a little bit of arithmetic back here. There's no fractions I need to deal with, right? That's just happening over here on the side. The little fraction stuff, that's just happening here on the side. I've set it up. I've set up my perfect square trinomial. So now let's factor that perfect square trinomial, which I know is going to be able to, since I am able to recognize this, I know it's going to be x minus 3 all squared. And then right here, 13 minus 18 is minus 5. Look at that. Now it's in that nice form that we know how to graph. If I was to sketch a graph of this, why not? Let's see. Where is its vertex going to be? Its vertex is at, I'll write it over here. Vertex is at 3, -5. See that from here, flipping the sign there, 3, and then keeping the sign here, -5. So that means I'm going to find that point, 3, -5. What else do I need to note about this? Once I have that point, 3, -5, I need to say, okay, it's pointing up. The parabola legs are pointing up because this is a positive 2, and since it's a 2, it's slightly vertically stretched. So instead of being a normal sort of parabola like this shape, it should be a little bit more narrow. Maybe like that. All right, so let me talk about this a little bit. I said that when you add a term, well, rather, when you have a term, a leading term that doesn't have a 1 up front, that it gets more complicated. But do you see where it got more complicated? It's not in finding the perfect square trinomial part, because the first step we did is to essentially like forget about the 2 for a moment. From this step to this step, the 2, so from this step to this step, the work is here. The 2 did not appear here, right? So when does the 2 complicate things? The 2 complicates things right here when you're deciding what needs to be subtracted outside of the parentheses. That's when the 2 has to get involved, which is what I wrote this statement about here. Okay, that's when the 2 has to get involved, or whatever the term here is, so that you have to account for the product of those two things being subtracted. Okay. Let's do another one. Okay, let me go find one from the homework. No, sorry, I flipped the signs. It should be plus and minus. Negative 3x squared plus 6x minus 2. Okay, negative 3x squared plus 6x minus 2. Okay, let's just try it. Let's just go for it. Let's just go for it and see if we can follow the steps from the last example. So first step, pulling this negative 3 off of just the first two terms. Okay, that's all I do for the first step. Pull the negative 3, pull the non-1 leading term, right? If it's just a 1, then I can skip this step, right? But it's not, so I need to factor it off. And the negative 2, you don't want a negative going on in here. That'll make things a little, you just don't want that, it complicates things. And of course, since I pulled a negative 3 off of the positive 6, it's flipping that sign, right? That's why that became negative. And then the minus 2, the constant term, just coming down. So I'm working with this thing off on the side, x squared minus 2x. What do I add to this to force this part inside here to become a perfect square trinomial? I take half of my b term, linear term, half of it, and I square it. What's half of negative 2? Negative 1. When you square it, you get 1. That's what I'm going to add inside the parentheses. So tell me, what am I going to add or subtract to the outside of my parentheses? So last time I said I'm subtracting, so I can go ahead and write subtract, right? And last time I did twice, or 2 times the thing I added, right? So 2 times 9 giving me that minus 18 out here. But now look, there's going to be a double negative, right? Because I've got negative 3 times 1, which is a negative 3, so I'm subtracting a negative 3. You see that? That negative 3 is coming from negative 3 times 1 there. And I'm still subtracting. So that means, yes, it is going to be an addition. In the end, this 3 is going to end up being added out here. It's just a consequence of this front term being negative. All right, next step. I know that negative 3 is coming down. I need to factor this. I need to recognize that as a perfect square trinomial. I do. I say it's x minus 1 squared. If this step from this part to this is giving you trouble, you need to go practice factoring perfect square trinomials, which is something that you can, it's section 0.6 or P6, prerequisite section 6 in the text, or you can just look up on YouTube factoring perfect square trinomials. You could find lots of good things there, or go to tutoring, right, through JSU, through the ACE department, and just tell them you need practice from this step to this step, which I haven't finished, by the way. Let me go ahead and write that down. Minus 2 plus 3 is plus 1 out here, right? So if you need help getting from this step to this step, then you need help factoring perfect square trinomials. Okay, so there it is. I've gotten it in this nice standard form here. I can go ahead and graph it fairly easily. I'll just go, I know I don't need to go too far on this because the vertex didn't move too much. By the way, what is the vertex? Where is it? The vertex is going to be at 1, comma 1, right? Negative minus 1, comma 1. All right, so that's right there. 1, comma 1. What do I need to note? What else do I need to note? I need to note the leading term is negative, so I should have my parabola pointing down. And it's a 3, so it's been vertically stretched. So it should be like fairly skinny, pointing down like that. Good, 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 good. All right, I think we are ready to do example 1 from the text. Example, in fact, we've already done the first part of it. It's kind of nice being able to record this up front because I can spend like way more time on this than I would be able to in class. Normally in class, I would not be able to work so many like preliminary examples. I would have to assume that you already know how to quickly recognize perfect square trinomials and things like that. So this is good. Let f of x, so this is going to be the same one that we did a second ago, 2x squared minus 12x plus 13. Part A says to express f in standard form. Well, we've already done that. It was f of x equals 2 times, what was it, x plus minus 3, what was it, minus 3 squared, all squared, and then minus 5. Hang on. Their graph looks, oh, never mind. They've got a, if you're looking in the text at figure 1, in fact, I can just show you, I got the text open here. Their parabola, this is their parabola. And look at the sketch I gave. It's quite different. It's much lower, right? So what the heck is going on there? They have the same vertex. I don't know if you can see that, but it says 3, negative 5. They just have a weird scale on their y-axis. You see that? See how each of these tick marks on the x-axis is 1, 1, 2, 3, 4, 5, 6. And this is 5. It's coming up by 5 on the y-axis. It's they shouldn't have done that, in my opinion, because now it just looks like a normal parabola when really it's like pretty low and it's pretty squished. You don't get that when you scale your y-axis differently than your horizontal x-axis. So I just want to point that out in case you're like looking at that picture and going like, why is that looking like that? All right, so we've already done part A. It was a fair bit of work, but there it is. We've already got it. Now part B says find the vertex. Well, that's easy because we can read it straight from this standard form, but it also says, and the horizontal and vertical intercepts, in other words, the x and y intercepts. You put dash x and y intercepts. All right, so let's do that now. So I'm going to write in purple the thing we already know, which is the vertex, which is 3, negative 5, straight from here, 3, negative 5. And now in red, I will do the part we're actually starting to, this is a new thing here now. So finding the x and y intercepts. Okay, I'll start with the y-intercept. Y-intercepts. Or only one y-intercept, right? If it's a function, it should only cross the y-axis in one place at most. If it crossed the y-axis in 2 places, it would fail the definition of being a function. So it should only have one y-intercept. It can have many x-intercepts, right? All right. Y-intercept. What do? We set x equal to 0. This is the easier one, to be honest with you. So f of 0, so setting x equal to 0 here, f of 0 is equal to 2 times 0 minus 3 all squared minus 5. 2 times negative 3 squared minus 5. 2 times 9 minus 5, which is 18 minus 5, which is 13. You could alternatively plug 0 into this, right, which you may find easier, whatever you want to do. If you don't like doing the arithmetic, plugging it into the standard form
then you can plug it back into the just generic polynomial function form they gave at the top and plug x equals 0 into that, and you just end up with that 13 at the back, right? The constant term. I'm not done here though. I need to write the answer. The answer is a coordinate point 0, 13. X is 0, y is 13. So when I draw my graph, when I drew the sketch here, this should eventually cross at y equals 13. So somewhere like up here somewhere it would cross the y-axis. Now, x-intercepts. That's going to be a whole new story here. And yes, I'm saying x-intercepts, possibly more than one. How many can this have at most? Well, since it's degree 2, since it's degree 2, at most it can have 2 x-intercepts. It could possibly have 1, or it could possibly have 0, but at most 2. So x-intercepts, let's look for that. What do? We set output equal to 0, the function output, or the y value, but in this case we're saying the function output equal to 0. So I write 0 is equal to 2 times x minus 3 all squared minus 5. Literally set the output, f of x, equal to 0. So you're setting the rest of the function, the actual function with x in it, equal to 0. What do? Solve for x. Let me go ahead and I'm going to flip this around because we like to have the x on the left. Okay, so all I did there was use the, well, I flipped it around. Okay, so what do? I can solve directly for x here. I don't need to worry about quadratic formula. I don't need to worry about factoring it. Like all the things that we talked about for solving quadratic equations in section 1.4, they don't really apply here. You don't need those techniques because if it's written in standard form, you can solve directly for x by scooting stuff across the equal sign, which is like the nicest way to solve for something, right? You don't need special techniques. Literally just keep putting stuff on the other side of the equal sign. So the first thing I'll do is add a 5 to both sides. I just need to make sure I don't mess up my order of operations here, right? That's what I need to be aware of. So adding 5 to both sides. Then I'm going to divide 2 on both sides. So I'm slowly unpacking this x. So I see there's still a squared thing and a minus 3. In what order should I get rid of these things? Well, x minus 3 is packed into the square function here, that squared thing. So I need to unpack that first. So I'll take a square root on both sides. And recall that when you take a square root in an equation, you want to add that plus or minus symbol to the front in an equation. Okay, this is an equation. So when you square root the left-hand side, the square root and the square just cancel each other out. And on the right-hand side, you're taking the square root of whatever's going on over there and you're putting a plus or minus in front of it. And you're leaving it. It looks terrible, but leave it just like that. Unless there's a perfect square that can be pulled out, but 5 and 2, neither one is a perfect square, right? So leave it, it's fine. Now last step is to add 3. If I'm going to add 3 to this, I need to, specifically the way I'm going to do that is I'm going to write whatever you're adding or subtracting over, write it up front. So the 3, it's positive because I'm adding it over, it's positive. If this was a plus 3 and I needed to subtract it over, I would put a negative here, but I'm adding it over, so it's positive. Then write your plus or minus square root part. There it is. Now, a good exercise might be to try using the quadratic equation on the original form we were given, which was 2x squared minus 12x plus 13, right? So that's a is 2, b is negative 12, c is 13. You will end up getting x equals, what do you end up getting? I'm crunching numbers, 6 plus or minus square root of 10 over 2, which does not look the same, but this is the same. These are the same. Yeah, I'll say this is the same. It doesn't look like it, but just trust me, like if you manipulated this the right way, it is the same. It's basically like dividing, well, you can see the 3 is there. 6 over 2 is 3, and then square root of 10 over 2. If I force that 2 under the radical, then I would end up dividing the 10 by 2 and also giving it another. I don't want to worry about that. Just know that these are the same. So 2 different ways of going about this, and I would obviously accept either answer. And WebAssign should as well, as long as you plug it in correctly. So 2 different ways of going about this. Use the standard form and proceed through, like I would say, normal equation solving techniques, like literally scooting stuff across the equal sign, remembering that when you square root something, you take a plus or minus, etc. Or over here, the more formulaic route, which is to start with the original form you were given and use the quadratic formula with a equals 2, b equals negative 12, and c equals 13. So a fair bit of, I skipped all the work here. You know, there's still a lot of work to get this cleaned up answer, but you know, whatever you like better. I'm guessing most of y'all would like this better, but I don't know. Okay, so what are these approximately? So I've got 2 x-intercepts here, x plus square root of 5 over 2, and that is approximately, if you plug it into the calculator and work it out right, you're getting about 4.58. And x equals 3 minus square root of 5 over 2 is approximately 1.42. So that means, what does this mean? What does this mean? Because I'm still, by the way, I'm still not done with this part, finding the x-intercepts. Not technically. I've done like pretty much all the work, but the last step is to say the x-intercepts are their coordinate points, right? So the x-intercepts are 3 plus square root of 5 over 2, comma 0. That's one of them, right? X value is crazy looking, but there it is, comma y value of 0, because that's what I set it as at the top. And 3 minus square root of 5 over 2, comma 0. Or approximately, if you like to have the approximate answer better, 4.58, comma 0, and 1.42, comma 0. Where are those on the graph? They should be where, let me write it down. This is where the parabola crosses the x-axis. So remember, I told you we would be going on a deeper dive into graphing these quadratic equations. This is one instance of what I'm talking about. We're going beyond just finding the vertex and deciding which direction it points and then just plopping it down. We're going beyond that and finding these extra pieces that help us graph it. In this case, finding the x-intercepts. So on my graph back here, remember, because I did a really rough sketch of this back here, my x-intercepts should actually be, well, they should be fairly close, but where should they actually be? About 1.42. So I got kind of, I should probably be a little bit more like right there, closer to the middle. And the other one is 4.58. So 1, 2, 3, 4. Oh, look at that. That's pretty good. Look, I did a pretty good job plopping down that sketch. But the point is that with this information, you could do an even better sketch, right? I kind of just got lucky, to be honest. I think I just got pretty lucky with these being so close, honestly. So let's finish this example. Part C says to sketch a graph. So let me show you how we can put all this info together. So recall, where are we at? We have f of x equals 2x squared minus 12. Yeah, minus 12x plus 13, which we were able to write at the top as f of x equals 2 times x, I've already forgotten what it was, minus 3, all squared minus 5. We found the vertex to be at 3, negative 5. We found the y-intercept to be at 0, 13, and we found the x-intercepts at their exact places, that 3 plus square root of 5 over 2, 0, and 3 minus 5 square root of 2, or square root of 5 over 2, 0. Those are the exact ones, but as approximate solutions, we got 4.58, 0, and 1.42, 0. So putting all this together, I can now sketch a pretty nice graph. So hang on, give me a second. Let me see. I need to think about fairly big y-axis because I want to try to get that y-intercept on there. All right. 7, 8, 9, 10. Okay, so that's up at 15, just to give me room to sketch this thing. I'll go down to 1, 2. It's negative 10 on the y-axis. So I'm being pretty careful about this. I want it to look pretty good. 5, 6, 7, 8, 9, 10. 10 for positive x and I don't care about this side as much. I know it's not going to be over there. Okay, start with the vertex. 3, negative 5. 3, okay, 1, 2, 3, 4, 5 over 3, right about there. Okay, next I'm going to write down these intercepts. A y-intercept all the way up here. I have an x-intercept at 1.42, so that's like roughly there. And 4.58, so 1, 2, 3, 4.5 right there. Okay, and what about another point over here maybe? Would that be helpful? It could be for sure. How could I find that? By the way, this is kind of like a side question. You don't need it, but this would be a really good thing to note. This parabola is symmetric around the vertex, right? It's symmetric around the vertex. So there's got to be another point. How far away, in terms of x distance, how far away is this point from the vertex? It's just 3, right? It's just in terms of x, not the height, just the horizontal distance. It's 3 units away. So what if I went out 3 units the other way? I should find a really nice point directly across from this. So just as an extra thing, find an extra point across from the y-intercept. So instead of going 3 to the left of the vertex, I'm going to go 3 to the right of the vertex. So I'm going to plug in. So 3 to the left of the vertex is 0, right? That was the whole point of that, right? So it's a y-intercept, right? So I'm going to plug in x equals 6, going 3 to the right, and I should get 13 again. It should be very nicely directly across, equal distance over that vertex. So plug in x equals 6. Let's see what we get. F of 6, I'll plug into this form here, is equal to 2 times 6 minus 3 all squared minus 5. That's going to be 2 times 3 squared minus 5. That's going to be 2 times 9 minus 5. That's 18 minus 5, which is 13. Nice. So I got an extra point just by noticing the symmetry, right? And saying, oh yeah, there should be a point that's just as far away from the vertex that's also at 13. 1, 2, 3, 4, 5, 6, 13, roughly there. You don't have to find it. Finding that was not part of this exercise, but it can be really helpful, and it's a good thing to note. There it is. Ooh, this is gonna be tough. Let's see. Shoom. Okay. Well, I guess I should. It's more like this. It doesn't go out more. There we go. It's a little, I got a little weird in here. It's hard to get these perfect, especially working under this camera where I am right now. And all that's expected of you as a student is to get a nice sketch and to also be able to write down this information, the vertex, the y-intercept, and possibly the x-intercepts. Why do I say possibly the x-intercepts? Well, because not all parabolas have x-intercepts. If this parabola was up here, like up here somewhere, it would never cross the x-axis. Or if it was down here pointing down, it would never cross the x-axis. That's a possibility for sure. Now, the last part of this example, part D, says find the domain and range. I'll point that out. All right, here is a fact. Here is a fact that you can use no problem. All polynomials. I'm spelling everything wrong today. What's new? Polynomials. All polynomials have unrestricted domains. Meaning their domain is the entire real line from negative infinity to positive infinity. So the domain in this quadratic function is definitely a polynomial. It's a very special type of polynomial. So its domain is negative infinity to infinity. The range, however, can be found by looking at the graph and deciding, so they'll have different types of ranges, deciding what y values or vertical axis values the function hits. All right, let's look at this. Okay, it never goes lower than -5, that's for sure. Does it hit every y value above -5? Yes, right? It's going to hit all of them. In fact, it's going to hit them twice because of the shape of this graph. So yes, it hits every y value above -5 and including -5, but nothing below. So how do I notate that? I say R for range. I say -5 to positive infinity. I know I need a parentheses around infinity, always. That's just a notation thing, always using parentheses around either of the infinities. And I'm including -5 though, so I'll use a bracket there. There we go, that's it. It's -5 and everything bigger. That's the y values this thing hits. Nothing lower than that. Okay. Let's see. It's 19th. One, two, three, four. Yep. Okay. So we are not done with 3.1 at this point. In fact, that was just example 1. But really, we've done like a lot of the work here. We still need to talk about maximum and minimum values of quadratic functions. But you will find that that will be much easier. In fact, we've pretty much already done the math for that. I just have to tell you some definitions, probably run a couple more examples. I do, however, before I end today, I want to do some special forms, getting some special function forms into standard form. And writing their vertex, x and y intercepts, basically everything I just did for that 2x squared minus 12x plus 13. So I'm going to say more examples. So for all of these, I'm going to want to write it in standard form. What else did that function? What else did find the vertex and the x and y intercepts, sketch a graph, and state its domain and range. All of that. So here we go. All right, let's start with f of x equals, we worked this one earlier, x squared minus 2x plus 3. Okay, standard form. I'll call this part A, standard form. I need to take f of x. I'll rework through this. We've already worked this, but I'll rework it quickly. I need to say minus 2x. I need to factor off any, well, oh wait, that's just a 1 there, so I don't need to do anything there. Good, so I can just think about what's half of negative 2 squared. That's what gets added here. That's going to end up being a 1. And then I have my plus 3, and I need to subtract that 1 back out. There's no shenanigans going on with a number multiplied out here that is going to adjust that. It's just plus 1 minus 1, right? This I need to know factors into x minus 1 all squared. I also need to know 3 minus 1 is 2. Okay, good. There's standard form. Awesome. Vertex then. The vertex is 1, 2. It's just coming straight from this form. C, sorry, y-intercept. Y-intercept is going to be plugging in 0 for x. So f of 0 is equal to 0 minus 1 all squared plus 2. Plugging into this. You could also plug into this and you'll see you should get a 3, right? Let's see if it works here as well. That's going to be negative 1 squared plus 2. Negative 1 squared is 1. So yes, 1 plus 2 is 3. So my y-intercept is 0, 3. Okay. X-intercept, or intercepts, let's see. I'm going to take the function in standard form, x minus 1 squared plus 2, and set it equal to 0. So x minus 1 all squared plus 2 is equal to 0, and I'm going to solve for x. Okay, good. X minus 1 all squared equals negative 2. Okay, just scooting stuff across the equal sign. X minus 1 equals plus or minus square root of, what does this mean? Square root of a negative. Hit the brakes, right? This is not allowed. This is not a real number. This is not a real number, right? The square root of negative 2 is what I'm talking about. Nothing to do, the plus or minus out here is, that's not relevant right now. It's this part that's a problem. This is not a real number. So this parabola has no x-intercepts. Has no, I should say no real x-intercepts, but since we're graphing it on a real number line, it has no x-intercepts. You could just say no x-intercepts, that's fine. Okay, that just means it doesn't cross the x-axis. That doesn't mean it's broken or anything. It just means that it doesn't have x-intercepts. Okay, part C is to sketch a graph. My vertex is at 1, 2, so I'll just probably go out to like 5 each direction. That should be plenty. One, 2, so x is 1, y is 2. There's my vertex. I know that it's pointing up. It's pointing up because the leading term, well, all the way at the beginning, the leading term is positive. So it's pointing up. I know that it has a y-intercept at 0, 3, so right there. And if I wanted to find an extra point, how far in the x direction, in the horizontal distance, how far is the vertex from this y-intercept point? Well, just 1. It's 1 away, right? The vertex is at x equals 1. The y-intercept is at x equals 0. So if I go over to the other direction, x equals 2, I should have another point at 3. If you don't believe me, plug in x equals 2 into this function, and you'll get 3. And there we go. That's so we can, we have enough to draw it there like that. And you see it does not cross the x-axis, has no x-intercepts, does not cross this x-axis. Okay, let me do another one. Oh wait, sorry, I was going to do part D here. Part D is stating domain and range. Domain is always going to be for these polynomial functions, just completely unrestricted. The range is restricted. What's the lowest y value it hits? 2, right? The lowest y value. And it is unbounded in the positive direction. All right, let's do f of x equals that negative 4x squared minus 12x plus 1. First step, part A, standard form. Standard form. I'm going to go through this quick. First, I'm just rewriting it. First thing I'm going to do is pull out a negative 4. Factoring out a negative 4 just from the first 2 terms. Remember, just from the first 2 terms. Now I'm taking this thing off on the side, the thing inside, and I'm saying, okay, I need to take half of my linear term. So taking half of my linear term here and then squaring it, right? Taking half of something means dividing by 2. So now I'm going to be adding a 9 over 4. Uh-oh, it's a fraction. That's okay. That can be done. That can be dealt with. It's going to be fine. So 9 over 4 is what gets added here. So negative 4 times x squared plus 3x plus 9 over 4. And there's going to be plus 1, plus 1. And then what am I subtracting? Well, I need to distribute this negative 4 in to hit this so that I know what I should be subtracting. Negative 4 times 9 over 4. Look, the 4's cancel, thank goodness, right? And I'm just left with a negative 9. So I'm going to be subtracting a negative 9. Subtracting a negative 9. All right, now, how the heck does this factor into a perfect square trinomial? How do I know? I know it's like x and probably plus because everything's plus in here, and then it's going to be squared, and back here this is going to be a 10, right? 1 minus negative 9. So, but okay, so I can do all that, no problem. But what about, what the heck is this going to be? It's a fraction, right? Well, back here, this number here, the thing that you took half of before you squared it, remember that's what ends up right here. So you don't have to think too hard about it. You can just write that number there. That's fine, 3 over 2. And then think about it. If I multiplied this out, I would end up multiplying 3 over 2 times itself, right? Doesn't that give you 9 over 4? And if I do x times 3 halves twice, doesn't that give me a 3? Like 2 3/2, that gives me a 3. So this works out. This works out. But remember that this term in here, this term right here, is going to come from the thing up here that you took half of before you squared it. The thing in right up in here. Now I'm ready to do what is next, which is to find the vertex. The vertex is at this value for x, but flipping the sign, so negative 3 over 2, and y value of 10. The x-intercept, or rather, I'll do y-intercept first because it's easier. Y-intercept is going to be 0. Look, how about I just go right up here and say, look, if it's in this form, your y-intercept, plugging in x equals 0, these go away. It's going to be whatever the constant term is. That's a lot faster than having to plug it in, right? Okay. My x-intercept, well, I'll probably get a new piece of paper for that one because that's going to be a bit more work. Okay, so I set the function equal. So are there shortcuts for the x-intercepts? Not really, other than asking a computer to help or something. All right, so I set the whole function equal to 0. I'm setting the standard form equal to 0. I'm going to solve for x. First thing I'm going to do is subtract that 10 over. Sorry, kind of writing out of order here. There we go, subtracting that 10 over. Now I'm going to divide by -4. Okay, let me clean that up. Let's clean that right-hand side up in this next step. So that's going to give me 5/2. Positive, right? That's a big deal to point out that this is positive now, right? Because now I can take a square root legitimately. Remember the last one, this thing over here was negative, and when I tried to take a square root, it didn't work. All right, but this will work. So x plus 3/2 plus or minus square root of 5/2. Finally, x is equal to, so remember, when you're scooting this last term over, you want to write it up front, and it should be negative because it's positive over here, so I'm subtracting it over, so it's negative, and then put your crazy square root thing. Okay, now you need to find the approximate values here, so I'm gonna write down the approximate values, like as decimals. So how do I do that? I'm going to show you. Do I have my calculator? Nope, I don't know where my calculator is, so I'm going to show you on my phone how you would do it. Let's see, can I get, can we see that, or is it completely washed out? If I tilt it, maybe it's this light doing it. Nope. I may not be able to show you with my calculator. I see if I tilt it, you can see it, but then you can't really see what I'm doing. It's like all washed out. Maybe if I turn my brightness down. Yeah, but then the light. Yeah, all right. So I'm going to have to do the calculation without showing you how to do it. But the way you would do it is it depends on what your calculator, how your calculator is. If you have a good scientific calculator, then you could do this like straight through. And remember, you're going to do one at a time. You're going to do the plus and then you're going to do the minus. So what I'll do, since I'm going to use the calculator on my phone, or actually I'm going to use the one on my computer, and it's not a great calculator. I have to do this first, 5 divided by 2. And then I take the square root of that, and then I'm going to say, okay, I'm doing the positive one, so now I'm going to subtract 3/2, which I know is 1.5. All right, so I'm getting one of them is the 0.08 if I round. And I'm going to do that again, 5 divided by 2, take a square root. So you see, depending on the kind of calculator you use, you have to kind of run things in reverse, which is super annoying. It's better to have a good scientific calculator. Now I'm going to negate that because now I'm dealing with the negative one, and then I'm going to subtract 1.5 or 3/2, which is the same as 1.5, and I'm getting negative 3.08. Good. So that was part B, finding the x-intercepts, y-intercept, and vertex. Part C is to sketch a graph. So my graph goes into the negatives a little bit on the x-axis. What was that y-intercept? Sometimes the y-intercept is huge. Nope, it's a 1. Oh, but my vertex is all the way up at 10 for the y value. So let me redraw this with a bigger positive y-axis. I don't need this huge x-axis, but that's okay. Okay, now I'm going to go all the way up to 10 here. 12. I'll go up to 12. So that's 12. This is -5. This is 5. And down here is -5. All right. So looking back at the data I have, I see my vertex is all the way at x value of -3/2, which is -1.5. So sometimes it's helpful to get those fractions as decimals just to help you know where they are on the graph. And then all the way up at 10. So here's 10 and -1.5, which is roughly there-ish. And then my y-intercept is all the way down here. So this tells me, I already know, but this tells me for sure that the graph is pointing down. I already know because that leading term is a -4, right? Okay, what else do I know? My x-intercepts, one of them is like barely like 0.08, so it's basically like really close to 0. And the other one is really close to -3, but a little bit past -3 at -3.08. I think that's enough to graph this. So I'm going to try my best to go whoop, and here. Okay. There it is, pointing down. Part D, domain, whatever, I'll do it in purple. Domain is completely unbounded, and range, this time it's pointing down, so it does not have a lower bound. Its lower bound is just -infinity, right? But it does have a highest y value. The highest y value it ever hits is 10. So your range is going to be flipped over when it's pointing down. All right, this is going real long, but that's okay. All right, let's do one more that's going to be a simple one. This is kind of one of those just weird special cases that's I want to go over. There, how about that? If it doesn't have a constant term, what do we do? Want to get this in standard form? Let me write it down. I'm going to say I need to add and subtract something to figure out or to get it factored into a perfect squared trinomial. So I'll take half of that linear term squared. That's what I'm going to add to both sides. So that's going to be -3 squared, which is giving me 9. So I'm going to add 9. I'm also going to subtract 9, right, for balance. Okay, this factored form here, remember, you can look at this step right here to decide what goes in the parentheses. So it's x minus 3 all squared. That takes care of these first 3 terms. X squared minus 6x plus 9. They all got compacted right here, and then minus 9. Okay, now part B, vertex is going to be 3, -9, recalling that you need to flip the sign in there to get the vertex. The y-intercept, plugging in 0 up here, 0, what's the output? Well, 0. That's nice. That means one of my x-intercepts should also probably be 0, because it has to be. If your graph goes through the origin, then one of them has to be 0, 0. For the x-intercepts. They have to share that intercept. But let's see, how would we do this? You would take the function x minus 3 in standard form and set it equal to 0. You would then start solving, so I'd say x minus 3 all squared equals 9, adding 9 to both sides. Then I'll take a square root, x minus 3, positive 9, no problem. Plus or minus, don't forget the plus or minus on the square root. Oh, look at this. This works out to be a nice whole number. Still with plus or minus, but square root of 9 is 3. Now, my solution, remember, I'm adding this 3 over, so it gets stuffed right there as a positive 3, and then I have plus or minus 3. Now, I can finish this all the way. I have x equals 3 plus 3, or x equals 3 minus 3. X equals 6, or x equals 0. So my two x-intercepts are 6, 0, and there's the one that I said should appear 0, 0. So there's my x-intercepts. I will let you guys graph this one with the vertex, 3, -9, the y-intercept going through the origin, and then the extra x-intercept at 6, 0. That one is not nearly as hard to graph as some of the other ones because we got nice clean x-intercepts. All right, so we will finish 3.1 together because this is the last recorded lecture, I believe, that I'll be doing. So we will finish 3.1 together talking about the maximum and minimum value for quadratic functions. And we'll also probably talk about modeling just a little bit, which means real life problems, just a little bit. All right.